Okay, so now that we have the squared differences between our home prices and our average home price, we can sum those squared differences to get the sum of squared total. Okay, so let's do that. Let's go up here to sum, and there we go. I'm going to round this just to keep it clean. And let's go ahead and highlight this and put sum of squared total. Okay. So very straightforward when using Excel. Let's go back to our formula. Now we know the sum of squared total is equal to these two things, so we got to derive them. So sum of squared regression is the sum of the squared differences between the predicted y, our predicted value based on our trend line here, and the average. So let's go back to this data point here. For this particular data point, we had an actual home value up here. But what would have been the predicted home value for a home of that square footage? It would be right here. It'd be along the trend line, y hat. So even though this square foot home had an actual home price here, we would have predicted based on our trend line a home price here. So we take that predicted value and we find out how far that lies from the average. See, y predicted, y hat, minus the average value, y bar. And then we square that, and we do that for every other data point in our set. So let's go into Excel, and we're going to create now another column, sum of squared regression. And we're going to put for that one, let me clean this up here. We're going to put for this one a formula. It's going to be equal to our predicted y minus our average. And I need to lock this because I'm going to drag it down. All right. And then I've got to square that. Okay. And then I'll just pull this down to get my values. And then I'll sum that up. Okay. And that's going to be, let me go ahead and insert here. Let me go ahead and put sum of squared regression, and that will equal this number here. Bold, italicized, there we go. So our sum of squared regression is 18,946. And then the last part of our formula is the sum of squared errors, or sum of squared residual. And for that, we're going to take our actual y value, our home price, but we're going to find out how far it lies from not the average, but from the predicted value. Square that, and then sum up all of those numbers. So let's go back to our data and create sum of squared errors. And now I want to create my formula. This is going to be equal to our actual value, home price, minus our predicted value. And I need to square that. That gets some pretty elongated numbers there. So let's round this as well. And then we'll drag that down. And same pattern, sum of squared errors. I'm going to put this sum here, add all these up, and I get 13,666. Okay. Oh, sorry about that. Oh, italicized. There we go. Okay. Now, if you did this correctly, then you should find that the formula holds up, right? That the sum of squared regression plus the sum of squared errors equals the sum of squared totals. So let's see if that's true. So let's take sum of, let's say equals the sum of squared regression plus the sum of squared errors, and we get 32,612. Well, that isn't the correct number. And the reason is because of rounding of our predicted value. So what I'm going to do now is put the more protracted version of the formula. This 98.248 we rounded, but it's actually 98.24833. Okay? And then this 0.1098 we rounded, and it's 0.10977. Okay? Now, if you do that and then recalculate your predicted values, you'll notice that everything gets rearranged, and now the sum of squared total from these two equals the actual value here. Okay. All right. The reason that I did that is because I want you to see how small differences in rounding can actually create larger differences in your results. So whenever you find that you're not getting the number that you should be getting based on the formulas, then go back and look at the rounding that you did in your manipulations. Okay, so to summarize what we've accomplished here, take a look again at our graph. We have a data point, right? And that data point shows a square foot home and the price that that home sold for. That home sold for a price that is well above its average. That difference is total variation. So that's part of our sum of squared totals. Okay? That variation has a portion that is explained and a portion that is unexplained. What do we mean? Well, for this square foot home, the average is here, but we would have predicted based on square feet this value here. So we call this portion the explained variation, right? And that is also known as our regression, sum of squared regression. So in essence, we've explained a portion of that price variation from the average based on square feet. But for that square foot home, even though the average was here and we explained that here, the actual price was up here. So this variation is unexplained. We could even make up some numbers. Let's say we have a 1,500 square foot home, and let's say the average price of a home in our data set is $200,000. Okay, and let's say this 1,500 square foot home actually sells for $300,000. Well, you would agree that that's a 100,000 variation, right? If the average price of a home is 200,000 and this home sells for 300,000, there's 100,000 in total variation. Now what we're doing is we're explaining that. And we do that by creating that trend line. So for a 1,500 square foot home, even though the average maybe is 200,000, let's say that we predicted that home would sell for 225. So that means you have 25,000 in residual, explained variation. You would expect that 1,500 square foot home to sell for 225, even though the average is 200 because of its square footage. However, you have this additional variation because a home actually sold for 300. So you have 75,000 that is unexplained variation. Where does that come from? Well, something other than square foot. And that's where we have to analyze a more expansive model to incorporate other factors that would influence the price of a home. This model only incorporates square foot. So we have a large amount of unexplained variation, errors. But when we get to multiple regression and we incorporate more independent variables, then we might be able to get less of this unexplained variation. That is, we might be able to reduce the sum of squared errors. And that's what regression is actually doing. Regression is sometimes referred to as ordinary least squared because what it's doing is it's trying to minimize this error. It's trying to find a line that it fits such that the error, unexplained variation, is the lowest number possible. What you've done is you've plugged in prices for homes and you've plugged in square footage, and you've effectively told Excel to create a relationship between these two that gives you the lowest sum of squared errors, the lowest of the unexplained variation. All right, let's move on. Another metric that is often used to evaluate regression is called the coefficient of determination, also known as R-squared. This coefficient tells us the portion of the total variation in our dependent variable, y, that is explained by the variation in the independent variable. So if we're talking about square footage as our independent variable and price of homes as our dependent variable, R squared is going to tell us the portion of the total variation in price that is explained by the variation in square feet. The calculation is the sum of squared regression divided by the sum of squared total. Well, recall that sum of squared regression is the explained variation, and sum of squared total is our total variation. So this is just a fraction telling us the proportion of the total variation that is explained. You can see this graphically. For example, if you have a data set that looks like this or this, you have data that perfectly aligns with your trend line, which means that the sum of squared regression is equal to the sum of squared total. There is no deviation of any data from your trend line. That's unlikely, but that would give you an R squared of 1. Now, notice that the trajectory doesn't matter. Here it's downward, which would give you a negative relationship between x and y, and here it's upward, which would give you a positive relationship between x and y. That has no bearing on the R squared, because the R squared is simply telling us how closely our actual data fits the trend line. An R squared of 1 is unlikely. What's more likely is an R squared between 0 and 1. And these two illustrations demonstrate how R squareds can differ. Notice, again, the trajectory doesn't matter. This just shows a negative relationship between y and x. This shows a positive. But this data here happens to lie closer to our trend line than the data here, which means this data set would have a higher R squared than this data set. What do we want? Well, we want a trend line that most closely fits the data. So we would prefer this kind of R squared versus this one, which means we prefer an R squared that's bigger, closer to 1, than smaller, away from 1. All right, let's now look at our data set and actually calculate the R squared. Going back to our square feet and home prices, we know that R squared is going to be the sum of squared regression divided by the sum of squared total. So we'll just put a formula in here. Sum of squared regression, and we divide that by sum of squared total, and you get 0.580841, which effectively means that the variation in housing prices, 58% of it is explained by the variation in square feet. Okay? Now, would we rather have a higher number? Would we rather have 60% or 70% or 80% of the variation in home prices explained by square feet? We absolutely would, because that would give our model more predictive power, right? It would allow us to use square feet to determine the prices of homes in the marketplace. But 58%, 0.58, is better than something less. Okay, now let's move on to Excel's regression tool pack. And this is going to help us get all this information that we just calculated in one fell swoop, right? Click of a few buttons rather than going through the details. We want to know how to do both because you want to understand where these numbers come from, but it's easier to get there with Excel's tool pack. To do this, you're going to need to, or I should say you may need to install Excel's tool pack. So I'm going to walk you through how to do that. If you go to Data, up here you see how it says Data Analysis? If you don't have that, follow these steps. Go to File, go down to Options, go down to Add-ins, find the Analysis Tool Pack, click Go, and then select the Analysis Tool Pack and click OK, and it will pop up there. You'll need to do that before we can proceed with the next steps. All right, That's it for this video. I'll pick up with Excel's tool pack in the next video. Let me know if you have any questions.